Okay, so I think we are ready to begin. So our first talk this morning is Nikita Nekrasov. So you want to pronounce the title yourself?
Okay. Well, good morning. Thank you all for waking up and for coming. It's a wonderful occasion to speak here. It's also a very tough one because I believe this is the third conference I'm with Pasha and Andrei this summer. And so I'm sort of running this month? No, we started in July, I think. And what do we know? Now
yeah, it was a summer school and two conferences.
Yes, okay. Not counting the previous 25 years where we were talking to each other a lot. So I'm kind of running out of subjects. But let me start with this diagram, which illustrates something. So when you start, you want to build a theory of everything. And then when you grow kind of more mature, you're ready to settle for the theory of something. And then quite often you get something of a theory. And then when you grow older, you start believing that that something of a theory you have is actually a theory of something. And then when you become classical, of course, the theory of something becomes a theory of everything. So this does not apply to neither Andrei or Pasha, but it sort of illustrates my relationship with this two. So
When you become classical?
yes. So that refers to the story which Ludwig Faddeev told actually many times. So when he was in the beginning stage of this diagram, and he was doing quantum integrable systems, in one of the talks he said that, well, but here I'm being classical, meaning that he was taking some classical limit when of large spin or small h bar, and maybe it was Ledezhenskaya or somebody really classical in the audience said, well, you're too young to be classical. So my talk is about the relationships between quantum and classical, and the way this correspondence grew out of my correspondence with Pasha and Andrei. Okay, so as I said, I'm sort of running out of subjects, so I will start with a subject which we talked about for the last 25 years in one way or another, and that's the elliptic. So by the way, in the theory of everything, E of course stands for elliptic, because that's more or less everything we talk about. And
I thought it was standing for me.
well, that's I mean, there is when I was working here, I passed by Harvard Medical School.
And E for me, but okay.
So the theory of Andrei and Pasha is this. I think it best handled in the building next door. So, so there are people who are paid very, very good money for that. Okay, so elliptical Algebra-Moser system. And of course, the minute I start writing names here, you're offending someone. So of course, if you replace elliptic by trigonometric, that's called Sutherland. And there are, if I add the adjective relativistic, that's Rosener-Snyder, and that will show up. So in fact, so one of the topics which I want to discuss is the relationship between the quantum elliptical Algebra-Moser system and classical Roizenars Snyder, and I'm sorry if I didn't capitalize enough. Okay, and but that so system also, sorry. Actually, the meaning of many words sort of evolves in time, and now one other comment which I want to make. Sorry, so it's everybody knows, especially everybody coming from the Soviet Union knows that when you are subject to constraints, you will function better. So when you have to be creative to avoid some obstacles, and of course the biggest constraint is the laziness of the brain. So when you try to understand somebody, but you just cannot, you try to find some ways to get around, and sometimes you invent interesting things along the way. But of course there are means of breaking through these walls inside the brain, and now there is a whole theory of wall crossing. And so there is some wall crossing involved in this relationship, but I'm just saying that there is so much more which is already known and said about the systems that I'm going to talk about, but I just wanted to say something maybe which we didn't talk a lot about and might return to one day. Okay, so what this is, so this is a system of particles. Now, when I was at the stage when I believed that I was building a theory of everything, I thought that these particles were living on an elliptic curve. But physically, you think of the particles as living on a circle.
But elliptic curve over real numbers can be assumed.
Okay, so I just hit one of the walls in my brain. So this circle is actually sitting inside the elliptic curve. So there is an elliptic curve somewhere. Of which, so these particles sit on some one-dimensional slice, and in the conventional physics setup, you actually want the elliptic curve to be real. So it's modular parameter tau to be purely imaginary. But mathematically, we can, and now physically, we can do various analytic continuations and study the problem where the elliptic curve is of generic type. So what is the problem? We want to say something about the spectrum of the Hamiltonian, the Schrödinger operator, which I will write as in this form. So I have two parameters here, h bar and m, and P is the Weierstrass function with periods 1 and tau. And as z goes to 0, it has a second order pole, and usually you normalize it so there is no constant term in small z expansion. By the way, if I write here, is it still okay? Okay. So the quantum problem is the problem of finding eigenfunctions and eigenvectors, for that matter, where psi are so psi should be an L2 function on the space of configurations of points on the real circle, And I think you want to divide by the symmetric group action. So for this problem actually to be, so there are some, there is a range of parameters. Well, usually in physics we say that h bar is positive.
And you want to divide by the SN. Usually even in this whatever it's called, in the trigonometric one, you allow like power to some, like when they're moving some power, something like this.
No, I think it's so the actual wave function when you write it as so one with some power, it's nice, but this power is I think should be positive, so that actually it vanishes when you approach diagonals, and then you continue it by a symmetric function outside the.
So the particles are ordered, so it doesn't really
Well, you can. So if you like, if you can avoid dividing by symmetric group, you can say that you just restrict the fundamental domain in some way. But
And you like the zero boundary condition?
yes. So for that, well, what kind of boundary conditions you want actually depends on the range of the parameter m. So when you approach the diagonal, small calculation shows that your wave function should behave as a. So let's say qi approaches qj. If I didn't make a mistake, it will behave as minus m over h bar, or the dual thing, which is probably 1 plus m over h bar. And so you want to choose between these two exponents. So one of them should have positive real part for the wave function to vanish at the diagonal, which physically means that the repulsion is so strong that the particles don't really want to sit on top of each other. And if your parameter is not of the form when the real part of either this combination or that combination is positive, then you have a phenomenon which in physics is called the phenomenon of falling on the center. So when you have the attractive potential or it's not repulsive enough, and then just writing this Hamiltonian is not enough to define the quantum mechanical problem. You need to supply additional boundary conditions, or you need to modify the potential at small distances. And somehow this should be reflected in the problem from which this equation can be derived, but I don't really know how this is reflected. Well, I'll get there.
So one of these exponents has to be small, or
well, one of the exponents should be should have a real part positive. So either and of course you can find the whole range of the ratios m over h bar for which this is not the case. So that's the bad case. Now,
but m in this ratio will be real, right? If you want the operator to be real.
not necessarily. No. See, once I relax the condition that tau is purely imaginary, so the spectrum will in general be complex valued.
Okay.
And,
What's the tau again?
so tau is a number in the upper half plane. And so in this picture, it's the imaginary period of the potential which you don't see when you only look at the particles. Now, I must say that once tau is complex and m and h bar are complex, nothing actually forces me to insist on particles to live on the real circle. I can choose any contour. Yes, I can choose any contour. And let my particles wander on that contour. So there are many quantizations of that Hamiltonian in that sense. And that will be reflected in what I want to describe on the right blackboard. Okay, so this problem is quantum because I wrote h bar here, well, it's because you see, so there is a non-commutative algebra of differential operators in Q, which you may at least locally you can make act with these differential operators on functions of Q, and so that's what's quantum about it. So there's something non-commutative, and inside this non-commutative algebra there's a commutative subalgebra, which H hat is one of the generators. There are other generators, so that actually you can pose the problem of finding the simultaneous eigenvectors of for this commutative subalgebra, and the fact that you have n independent differential operators for the system of for functions of acting in the space of functions of n variables. That's an intuitive quantization of the notion of a classical integrable system, where you have on the symplectic manifold you have the maximal set of Poisson commuting functional independent functions. So that system is actually a quantization of a classical integrable system, for which you can read off this Hamiltonian simply by replacing the differential part by the sum of the squares of momenta. But interestingly, this system has a generalization which also is related to the gauge theory problems, which I will talk about later, which does not seem to have a classical limit, and that's an interesting possibility to stay young forever. So it's if you want to stay young forever, here is what you do. So you add another set of particles. So here we have particles in the amount of n, and now and now. Okay, so here's what I'm going to do. I will change the notation. So from m I will now m I will replace by h tilde. So far I didn't do anything. I just divided my Hamiltonian by h bar. So let me just change the notation. And now I will introduce another set of particles, q tilde, which live on the same contour, which will have a. So first of all, they will have their own kinetic term. So this is outside the bracket. And then here h over h tilde Well, except that they didn't know about elliptic. I mean, they knew about elliptic functions, but they didn't know that the system allows the elliptic generalization. So indeed, if you degenerate elliptic curve sent out to infinity I infinity, that will be exactly the system that Veselov and Sergeyev studied, and that has some relation to super Lie algebras. And actually, I think so the reason I wrote this is that I believe it also has a relation to what Misha Finkelberg was talking about, even though I couldn't really understand what he was talking about because I was watching it on the, not just because I was watching it on on the computer, but let's say because of that. But I think we should discuss it, and I believe there's a relation. Now,
Actually, what definitely is related to is elliptic double affine algebras, which Eric will talk about.
good. Okay.
And also if the solution of this VDDW generalized, which is about twice.
What is VDD?
I mean this Frobenius type.
I mean W
Yeah,
dv.
okay.
Well, that I don't know. I don't.
Anyway, so you can prove integrability of this by using shading algebras on elliptic fields.
Yes, so there is a, I mean, in more down-to-earth terms, there are Dunkel operators for the system, which were written down explicitly. But you can, so there is a setup, there's a class of problems in which this kind of, from this problem also arises naturally, for which you can get the expression for the.
You get that stuff from, so if you want the non-elliptic function, you get it from partitions, like it's hoops that have like m rows going here, m columns going there.
So that's.
Is there an elliptic weight on partition that you can quantify?
Yeah. So this is how you can get it by reduction of usual algebra when you have two sets of variables, but there is one of the sets is many quarters.
No, what I mean is that there is a discrete.
That's probably for integer ratio. Probably.
There's a discrete equation that comes from that in the limit gets, well, you know that stuff. So if you have a partition that fits in a hoop, then there's a discrete integrable system that will give you not the elliptic, but rather the Jack version.
So there are super Jack polynomials for which are the eigenfunctions of a trigonometric version of that. Right. Well, and also the partitions which fit in the hook, I think they label representations of GLM/M. So that's one of the reasons why it's related to the superalgebras.
Yeah, you're right. It can be done for integer m this way, but for non-integer m, you can do it in the Lie case the same way.
Okay, so that's actually one of the interesting topics that Pasha always tells me about when we talk pretty much about anything. But and last time when it took maybe several weeks was in 1997 when you were helping us to, or 98 maybe, to find some conformal field theories in 4 dimensions related to discrete groups. And I still have a wall in my brain which I cannot really penetrate, but I think I found a way around it. So I don't need to think about the category which sort of analytically continues the category representations of a group. I have other means of getting this system, but they might be related, and so I'll explain. I just wanted to say that. So in this system, you can send one of the h's to 0, h or h bar or h bar tilde, and so one of the sets of particles will sort of become classical, will evolve according to a classical Hamiltonian system, but the other set will remain quantum, and so you can play with this game forever. Yes.
If h bar and h bar tilde are same, is there some interesting thing happening?
So if you try to send both of them to 0, they let's say keeping the ratio finite, it doesn't seem to lead to a nice limit. So usually the wave function scales as 1 over exponential of 1 over h bar times the classical action. But here it will appear that you need to scale it like 1 over square root of h bar if you want to send both to 0 with the same rate. And that's a new kind of asymptotics which I don't understand really.
No, but actually when they're equal to each other, this was the question.
Yeah.
But it's just
usual algebra for a particular value of m equals
there might be minus sign actually. If I made a mistake in the writing, then it's not going to be the usual calogera. No. Because I mean, super here is not an accident. So there is some the coefficients here have to. So let's put it minus. The coefficients here have to do with the usual root approach to a calogera system. There is some the coefficients have to do with the norm of the roots, and so for the super algebra, there is a change of sign. Let me double check. Actually, no, I'm sorry, you're right. So it's plus.
It's the usual calogera in that case. Because for integer m over h equal 1 and integer m, it appears that you have.
So a cluster. You can
m copies.
Yeah, you can make clusters.
So if m equals 1, this is just means that all variables have equal root.
Okay. Right. So sometimes people say that this describes particles of two masses. And so you can create particles of higher mass by clumping smaller particles together. But again, for me, these are actually complex parameters. So I don't really want to analytically continue from integer values. Okay, so the right-hand side, I only know because of the I only know the right-hand side for the m equals to 0 case. And so here we take the classical Roisener-Snyder system, also known as the system whose one way of characterizing Macdonald polynomials. In another gauge. So the way to think about it, one possible way to think about it is to consider the moduli space of flat, let's say SLN connections on the two torus with a puncture, with a special conjugacy class with of a monodromy around the puncture. So the monodromy around the puncture should have the maximally degenerate, maximally non-trivial degenerate eigenvalues. So there are n-1 eigenvalue equal to t, and the last one, which is just compensates making an SLN connection.
So the m is not the same as that m, right? M equals 0, then this
is yes. Thank you.
But n is the same as the n before. Yeah.
And that n is the same n as before. Okay, so this is a symplectic manifold, and what it is, so it's a space of pairs of matrices A and B, which solve. So these are the monodromies of my flat connection around, say, an A cycle and a B cycle, which on the torus, which don't. So I choose the cycles which don't pass the puncture, of course, and they obey an obvious relation, which modular some changes of signs says that the group commutator is equal to m. So that m, and we identify the pairs which are obtained by simultaneous conjugation. So now it's kind of it's obvious. Well, so the functions on this modular space are built as follows. You take any loop, any element of fundamental group, you compute the corresponding monogamy, and you take it, let's say, trace or its eigenvalues, and so that will be a gauge, that will be an invariant function, and you can compute the Poisson brackets of these functions almost geometrically by looking at how the cycles intersect and doing obvious manipulations. And from that, it's kind of clear that, let's say, if you take any simple loop and take the holonomy around that loop and take its powers, for example, trace a to the k, for k equals 1 to n, this will be Poisson commuting. And now, another simple exercise, well, just it's not difficult to show that this space has dimension n for generic T. Sorry, this modular space has dimension twice n minus 1, namely, and you can parameterize it by, let's say, the eigenvalues of the holonomy around the A cycle. So we can go to the gauge where A is diagonal with eigenvalues A1 through AN, and the product is equal to 1. And now, from this equation and from that condition, we'll actually determine B uniquely up to a multiplication on the right by a diagonal matrix. So that's something diagonal in that basis. So B is determined from this equation uniquely up to the multiplication by a function of A. Right?
If AI,
Well, any function of A. So.
if AI are not equal to A.
Right. I mean, this is always the case. So B is that's the ambiguity in determining B. But if AIs are distinct, then up to that's the only freedom. And so you can in fact explicitly you can find B to be so there is a convenient gauge in which B has a form where B tilde is Bi So now, so if I parameterize my modular space so by the coordinates A and B, AI and BI, one can show that the Poisson brackets are canonical, and so the Rosiner-Snyder system is a system where the variables, the coordinates are A, the momenta, or rather logarithms of A, the momenta are logarithms of B, and the Hamiltonians are the traces of powers of B. Now, because B is an invertible matrix, usually people write as a basic Hamiltonian the analog of this Hamiltonian is not H1 or H2, but rather H1 plus H minus 1. And so that turns out to be, so this is a relativistic Calogero-Moser system. Relativistic trigonometric.
But McDonald operator is just H1. The one that McDonald used.
So they are the quantization of this one.
Yes.
Yes. So if you now replace if you now realize B as a shift operator by namely quantizing it, it turns out that you don't need to worry that much about the ordering. So there is a well, McDonald worked it out.
So this is just to make it real.
So the square root, yes, it's to. So this is so-called unitary choice. When T is a pure phase and A's are pure phases and B's are pure phases, then it will be a Hermitian operator. But again, now for me this is all complex, and so the claim I want to make, even though I cannot prove it, so it remains a conjecture, is that the spectrum of this system, let me erase now, this with M, is determined by the classical geometry of that system. So the quantum spectrum here is determined by classical geometry here. And what is the classical geometry? Well, in this moduli space, so it's Mn of T. As I said, it's a symplectic manifold, and on the open set where the eigenvalues of A are distinct, I actually parameterize it by the Darboux coordinates, well, the logarithms of A and B. So in this phase space, we need to study certain Lagrangian submanifolds. Say it again?
Have you already formulated the concept?
No, I'm just explaining it. No. So there are. So this is the symplectic manifold of. Here are my A coordinates and here are my B coordinates. And now I need to define two Lagrangian submanifolds of this in this modular space. So the first Lagrangian submanifold will be I use the word the brane. Now it's different brane. It's a brane in string theory sense, but geometrically it's just a Lagrangian submanifold of opers. So the opers are the nth, in this context, these are the nth order differential operators. So nth order differential operators. Now, in order to define this Lagrangian submanifold of operas, it actually depends on the choice of a complex structure. So far here, I was not only classical, I was also topological. So I only needed the torus as a topological space. Now it turns out. So now I want to say that inside this modular space, which is defined in topological terms, there's a bunch of Lagrangians which are parameterized by choice of a complex structure on T2. So once I identify my T2 with an elliptic curve, I can study differential operators, which are holomorphic or meromorphic differential operators in this complex structure. You don't need U1, so U1 can be set to 0. So U2 and U1 are allowed to have a pole at this puncture. So let me call this point V equals to 0. So I think UI may have a pole of the order. So when z goes to 0, such that so the monodromy of this differential operator around this point is conjugate to what I just erased. So this operator D has a regular singularity at z goes to 0, with the only local solutions behaving as either z to the power m or.
I'm not sure if
Actually.
the numerator is correct. Is it m to the really m to the I? For example, if you have n equals 2, you are supposed to get m times m plus 1 over z squared.
You're right. So it might be after. It
There
may
are
be.
some polynomials.
Yeah. Okay.
M. which-
Yes. So I should rather write that locally D should behave as.
Just some constant over z to the I. Ci over z to the I.
Well, I want to make sure that, so these are my local solutions. So there should be a way.
Right. So the constants are such that local solutions will be this way.
Right. Or maybe to match to what I had over there, it would be like that. And so the multiplicity is, so so most of them should have one behavior and one should have another behavior.
This is good.
Okay, so now when you analyze the conditions on the functions which this restriction imposes, because you have fixed the polar structure, there's just so much freedom that you have. You can add some constants, and the actual number of these constants is exactly n minus 1. So the space of such D's is n minus 1 dimensional. So in the simplest case, n equals to 2, when n equals to 2, such operator will have the form I think plus a constant. So the polar structure is fixed to be the Weierstrass function with a prescribed coefficient, and the only freedom is the choice of constant.
You need to divide by 2.
I don't want to divide by 2. I don't want to divide by 2. I want to put my s.
So this is the Lagrange is just the image of monodromy of this eigensystem, right?
Well, you see, here we have the problem of we have functions of n variables, and here we have only one variable.
No, but I mean there is this Dirichlet theorem, which this is a kitchen system, and so
Okay.
you have.
Right. So that's.
So actually, on Monday, Edith Franklin talked exactly about this business.
Good.
In
Good.
a more general setting, also with conjectures.
Okay. Okay. Very good. Yes. Indeed. It sounds like it's the old story, because indeed this is so if you don't care about the fact that you want these wave functions to be normalizable, I mean L2 or anything, if you just look for formal wave functions, then the spectrum, so the set of the eigenvalues which are parameterized by some formal spectral parameters, is exactly this Lagrangian of operas. And the tau which appears here is the tau which you need to fix here. But
You're saying that you don't know what this conjecture.
I don't know how to prove this conjecture. I didn't say the conjecture. I didn't state the conjecture yet. I didn't
The
state
fact
the.
that this coincides with monodromy is theorem of Bayes and Madrid.
Well, not exactly, because Bayes and Madrid. Well, if we are now being mathematical. Bayes and Driefield consider the Riemann surfaces of genus starting with 2 with no punctures. So this is so. It's but of course, morally, it's the same statement. Of course, again, if you formulate everything, at the level of abstraction that they do, it becomes probably a tautology, and so there is nothing to prove. But it seems like there is no content even. But I claim that there is some content to this statement, and in particular, the reason why I brought up the Reusener-Schneider system. Did Edik talk about it?
Edik, not about this case. He talked about in general.
Okay. In general, okay. So there is
Spectrum for quantum Heat system in general.
good. There is some reason why I introduced this coordinates A and B. Namely, Lagrangian submanifolds are so if you write them, if you describe them in Darboux coordinates, they have a generating function, and that's something which I want to say we have means of computing, which is not the case for the general Hitchin system. And so this subvariety is described by the equation that bi is equal, so b, which I introduced and erased, is exponential of some function w, which depends on a and actually I should probably change notation. So let me call ai exponential of alpha I. So w will depend on m, on h bar, and on tau, and on alpha. And so the first conjecture is that I will give you a formula for w, and so that w will be the generating function of the variety of operas. And the second conjecture is that to describe the special to describe the actual spectrum corresponding to the physical problem being that you want the L2 normalizable wave functions, or some analytic continuation of the notion of L2 normalizability, which I don't know in general. You actually want to intersect that Lagrangian with another Lagrangian submanifold. And the choice of a second Lagrangian, so let me call it L topological. So that correlates with the choice of the contour. And so that L topological is described as follows: that you take the contour, and to be honest, I'm not yet sure whether I choose that contour or one of the dual contours in the sense of symplectic pairing, and I require the monodromy around that contour to be trivial. So that also imposes n-1 conditions. So all eigenvalues being 1, and so in the
So the conjecture is that for every choice of contour, you have some L topology
Yes.
of gamma, where gamma is this contour.
Right.
And then you take set S gamma, which is intersection of L with L topology.
Exactly.
And then you take the union of all those sets.
No. Just so every point of intersection is a point on the physical on the discrete spectrum.
Right. So, but Nikita, can't you just make this contour to be like a horizontal contour that will give us your own condition?
Yeah. So one of the choices would be just to say that bi is equal to 1.
Okay. So you choose a gamma, then you define the spectral problem, and then
Yes.
eigenvalues are parameterized by this intersection.
Right.
Well, I'm saying that this is, if you solve the problem for one contour, then everything else will be the same.
Well, you need to do some Legendre transforms with W to pass from one polarization to another polarization. So It's more. Now there is one. Unfortunately, it's not a complete form of the conjecture, because sometimes it seems like that you may have a contribution of holomorphic disks, which may correct some of the statements. So sometimes, if you can see that actually in doing conventional quantum mechanics, the spectrum exhibits so-called splitting behavior. So well, I don't.
Some problems here that correspond to the actual Flory complex on the other side.
So I'm saying that splitting seems to come from the contribution from the non-trivial non-trivial Flory differential, but this is not yet completely established. So
this is actually very close to the conjecture that Edith made.
well, it's a kind of a consistency check, I guess.
No, I mean, actually,
but
the paper with Kashdan and,
yes.
and me, which appeared on Monday, which where this conjecture is stated, and it's not exactly this, but it's really related.
Okay, very good, very good.
It's really related in the sense of real amount or something.
Well,
Yes, because there they in this instead of polynomials, they would have Lagrangian where the monoid was real.
Yeah, no. So the other, in our case, we are studying common eigenfunctions of cohomology and complex conjugate.
I see.
And then the other Lagrangian is just complex conjugate of L.
Well, there is another class of problems which are, let's say, best studied for n equals 2, where people are interested in, let's say, metrics of constant curvature on the Riemann surface, and those translate to indeed the intersections of the Lagrangian of Hoppers with let's say SLN-R flat connections or SL2R flat connections, and that's so these will translate to the equations on the real and imaginary part of W.
So this is the what they do.
Okay, so that's more that's another aspect of this another application of this geometry. Okay, so now in my work and in my work with Andre, so that type of problems. So originally I was interested in these problems themselves, and then they were too difficult to solve directly, and so then I got distracted and started to work on instantons and gauge theories. But apparently the subconscious works in mysterious ways, so it turns out that to be related to the same problem. So, and how am I doing with time?
You have about 5 minutes.
Okay, thank you. You know, another mystery of the subconscious is that the time on the on the inside can flow at a different speed as the outside. But you really need some helpers for you to. And I'm not talking about mushrooms. It's.
What's the signature of your metric on the inside?
I think it's no. I don't think you can change the signature. It's just it's a different what's it called? The scale factor or. All right. So instanton counting. And okay, there were already many talks about this in this conference. So I'll just draw a cartoon, which is okay. So you know, one thing you need to measure time, you need to cross your timeline with something. So that's the way we measure time. And so crossings are important things. So here I'm crossing four complex lines in the four complex dimensional space. And so you can set up kind of a generalized gauge theory problem in which you have gauge theories living on two-dimensional planes sitting inside this four-dimensional vector space, and that should be viewed as a model of a more general surfaces intersecting inside the Calabi-Yau form. And so the problem which is related to this discussion is the one where you have a stack of, so you have like rank n 1, 2 sheaves, torsion-free sheaves which live on C2 with coordinates Z1 and Z2. I mean, the sheaves are actually living on projective compactification of the plane, and they're trivial on the line of infinity. And so what we do, we integrate over the modular space of the sheaves. So this is Giesecke and Nakajima space. The rank is n1, 2, and the second Chern class is k. And so we consider some generative function. So n1, 2 is actually n, so I will not write this. The same n as before. And here you have something like the Euler class of the cotangent bundle. Well, it's the equivariant Euler class, so it's a Chern polynomial, and the argument of the Chern polynomial is going to be m.
So is it the same as the ADHM, a modular space?
It's the ADHM modular space with a shifted stability condition. So it's in the notations of Andrei Smirnov talk yesterday. So he had eta. We call it zeta, but it's non-zero. So the moment map equation, or the real part of moment map equation, is taken to be at non-zero value for the ADHM. And so the integrals is equivariant under the respect to the two-dimensional torus section on C2, 1, 2, with parameters epsilon 1 and epsilon 2. And now m should be viewed as a parameter epsilon 3. So this counting actually comes from a more general story, which is naturally associated to the four-dimensional vector space, on which you have the action of the three-dimensional torus, which acts with the weights epsilon 1, epsilon 2, epsilon 3, epsilon 4, which sum up to 0. So it's a torus inside the group SL4.
So moment map is not 0, but the moment map is like commutator of x and y. So
Okay, let me write this explicitly. So the complex moment map is 0. And the real moment map is not 0. But actually, so to explain the origin of this factor, you need to, these equations are generalized. So actually, the equations which we are solving they are kind of more involved.
But in terms of algebraic geometry, this space, how does it differ from ADHM?
Well, in general, it's not an algebraic variety, actually.
This mgn of nk is not an algebraic?
No, okay. So this is an algebraic variety, but it sits inside.
This was explained in the whole week of lectures on the topic in July.
Yeah, but I missed those.
Oh, okay. So that's what I should have been talking about. But okay, my time is up. Anyway, so this generating function, when epsilon 2 goes to 0, has the asymptotics which is identified with this W. And so m is epsilon 3, h bar is epsilon 1, tau is this Q parameter, and alphas are the equivariant parameters for the framing group GLN or SLN, PGLN. And finally, so once you understand, once you have this more general setup, you can actually throw in the second copy of the gauge group. So second gauge group for sheaves which live on the neighboring plane, C23. And so then the corresponding generating function will produce these two species Cayley-Moser system. And from that point of view, the fact having the ratio m over h bar being an integer means that instead of having the maximal three-dimensional torus as your symmetry acting on this space, you choose a subtorus which you embed with some integer slope inside this torus. And what the significance of that for the relativistic formalism, I don't know. I know at the level of formulas that there are some simplifications, but I don't know how to make the full advantage of it geometrically. Well, I didn't get to talk about another instance of classical quantum correspondence, which I just want to mention it. So there is an interesting work which was initiated by Gamayun, Yorgov, and Lisovy, which connected the tau function of Penlevet-6 equation to the C equals 1 conformal blocks of Liouville theory. So the tau function of Penlevet equation is something which I would call classical, because it's a tau function of a classical integrable hierarchy. And C equals 1 conformal blocks are something which is extremely quantum. So it's very deep in the, it's not C equals infinity. And the gauge theory approach to both sides of the relation actually allows to get some explanation for why such relation exists, and that has to do with the blow-up formulas in gauge theories. When you compare incident counting on this complex surface and the surface blown up at one point. So to conclude, it's helpful to think about these problems which appear to belong to a two-dimensional world or one-dimensional world using a 4 or 2 or whatever higher dimensional perspective, and vice versa. And in my journey on subjects, the correspondence with both Andrei and Pasha was always very inspirational and helpful, and I would like to wish them a happy birthday.
Any questions? You promised the formula for W.
That's the formula for W. Well, okay, it can be made slightly more explicit, but not too explicit.
So W is the limit of logarithm of this left-hand side multiplied by epsilon.
Yes, so the left-hand side is written as the sum of the antuples of partitions. And in this case, it will be the sum over n plus m tuples of partitions. And then in the limit epsilon 2 goes to 0, there is some kind of limit shape phenomenon which happens. So there is some configuration of partitions of very large size which dominates, unlike the limit shapes which Rick was talking about and Andrei worked about, which are nicer kind of geometrical structures when both epsilon 1 and epsilon 2 goes to 0. These ones are, I mean, they're not very nice shapes. They're kind of, but they're semi-classical nevertheless. So they look like more, I think it's called mica, sluda. What's the English word for it?
Yes.
Mica, yes. So they have this mica-like structure. And one way to describe them is using the limit epsilon 2 goes to 0 of QQ characters, which become Q characters of Frankel-Schutichen. In this case, they become Q characters for toroidal algebras, and so they're not very easy to analyze. But that's one way to characterize these equations.
So do you expect that there is a similar conjecture in a more general setting of quantum Hitchin system? The formula for W, for example.
Well, as you know, the trouble with the general Hitchin system is that we don't know the gauge theoretic description of that. So Hitchin systems for SL2 already for the SL2 for higher genus, there is one stumbling block, namely So we need to somehow to learn how to work not with this Giesecker compactification, but with Uhlenbeck or maybe a finer compactification of the module space of instantons, which does not replace bundles by sheaves. And so far we haven't made much progress.
But it does come from gauge theory. You expect that.
Yes, yes. So that these cases involve it's most genus 0, genus 1, and genus in genus 0 these are the so-called linear quiver theories, for which we have a good control.
Genus 0 was tame ramification with parabolic structures. Yes.
Yes.
Arbitrary parabolic structures.
Well, it works best for regular. Well, okay. So it works best for the cases when you have two regular punctures and an arbitrary number of so-called minimal punctures. Then
minimum means that you have this kind of
n minus 1 multiplicity.
T to the
Yes. Then once you that way you can define your partition function in one domain, and then by analytic continuation you can generate an arbitrary puncture out of the by coalescing minimal punctures. But that sounds like a very hard analytic work. So there should be a better way of doing that. So one direction, one help might come from the duality to topological strings. So instead of dealing with curves, you can deal with toric Calabi-Yaus. And then again, there is a kind of heavy machinery which Andre and I proposed, but it's again in practical computations, it's not very. I mean, I don't know how to make it really a very good computational tool. Let's say already the simplest case, which is hard for W algebra people, for SLN on a sphere with three regular punctures. So there is a dual geometry to that, dual Calabi-Yau geometry, but it's also kind of involves. So then you split it into lots of triple vertices. Get some kind of hexagonal structure with lots of faces, and then each vertex comes with three-dimensional partitions. And so you need to make a sum of all these partitions. And well, but just get something concrete out of it. We're not afraid, but
let's have one last question, and then the rest of the questions.
Does it make sense to make the both sides non-stationary by introducing the derivative with respect to tau?
Okay, good question. So, so there is an object, of course, which so if epsilon 2 is finite, if we don't take a limit epsilon to 0, so there is there's an object which I mean, one way, which probably not the most general, and so maybe now that the theory of elliptic the stable envelopes is developed, maybe it will be generalized. But the current stage of the art is that you do it using orbifolds. So if you now introduce a certain cyclic group acting on the space, the partition function of the orbifold theory will satisfy the non-stationary equation on the left-hand side. And then there is a mirror of that, which... Yes, the KCB equation. Yeah. So the analog of k plus n, more precisely, is epsilon 2 divided by epsilon 1.
Okay, I think the rest of the question will have to be in private. So let's have a break. We'll reconvene at 11.
Thank you.
Okay, actually, let's make it a little later. Let's make it 11:10.